Algebra 2 Honors 4.5a and b. These are the notes for 2 days worth of homework. And so let's get started. We're going to be solving polynomial equations. So we're going to be finding solutions and zeros of polynomial functions. We're going to be looking at something called the rational root theorem and the irrational conjugate theorem. And so we have an example 1 to solve this polynomial for where it equals 0. So you need to have algebraic work. Start by copying that problem down. And we're going to start by trying to factor this to find the zeros. So we can pull out a 5x. Notice writing the equation that equals 0 on every line. And this happens to factor x minus 4. And so that is x minus 4 quantity squared. And so we think of 4 as a repeated solution. And your solutions to this are going to be x equals 0 and x equals 4. Those are my solutions. That's what's going to make that 0. And notice this was a 5x cubed. It's to the third power. So the 0 counts as one of the solutions, and the 4 counts as 2 solutions. That's what we're going to think of it, so that there's a total of 3 solutions since it's a polynomial of degree 3. And so then another thing that we've studied is end behavior. And since this is of odd degree but a positive leading coefficient, overall, I expect the graph to look something like this. So that as x goes to negative infinity, y is going to negative infinity. And as x goes to positive infinity, y goes to positive infinity. And so we're going to sketch a graph of this using this information. We have a 0 at 0, and we have 1 at 4. And so when I had that repeated solution and it's to an even power, so not only is it a repeated solution, it's repeated an even number of times, I expect there to be a bounce at that value of x equals 4. So it's going to look something like this. So it has to come from negative infinity. It's going to pass through at 0. So it's going to come back down, polynomial smooth curve, hit at 4 as a 0, and then go back in the same direction it came from. The y-intercept on this is just 0. When x is 0, y is 0, so there isn't another y-intercept to consider. And how high it goes between 0 and 4, I'm not really looking for that to be super accurate. Just that it has the characteristics of the correct zeros, and you treat the repeated solutions correctly, and the end behavior is correct. So there is a sketch of that graph. And so the idea on these problems is you are analyzing it according to zeros and repeated solutions and behavior. You're not going to Desmos to get the solutions of the graphs or the back of the book. It's really important that you analyze these and understand the characteristics as they play out. Now, a little bit on vocabulary. The 0 and 4 are known as both roots, zeros, and solutions to this polynomial where it equals 0. So those are some terms you need to be familiar with. Example 2a, find the zeros of this function and then sketch the function. And so on this one, it's quadratic in nature. The exponent of 2 is half of the exponent here. And so it's quadratic in nature, so we can factor x squared, two numbers that multiply to be positive 81, add up to negative 18 or minus 9. And we're finding 0, so set it equal to 0. And then each of these are differences of squares that factor x plus 3, x minus 3. So in this one, you have 2 repeated solutions. You have x plus 3 quantity squared, and you have x minus 3 quantity squared. Again, they are repeated, and they are repeated to an even power. So you expect that there's going to be a bounce where the graph comes and hits at those zeros and goes back in the same direction. So my solutions, the zeros, actually I'll just write zeros, are x equals -3 or x equals +3. And for end behavior, since it's x to the fourth, but it's a +1 as a coefficient for that, we expect, oops, both ends to go up to positive infinity. So both as x goes to -infinity, y goes to positive infinity. As x goes to positive infinity, y is going to positive infinity. And so we have at -3, and at 3 we have a 0. The y-intercept, f of 0, is 0 minus 0 plus 81. So it is at 81. And so this is a 10 by 10 grid. So if I go by tens, and that would put that y-intercept about here. And what happens on this one is it comes down, bounces at both -3 and +3 because of that even power. If it's to an odd power, it will pass through at that 0 and change from negative to positive or positive to negative. When it's a repeated factor to an even power, it does the bounce kind of thing. So let's look at this next one, find the real solutions. So set it equal to 0. And factor, use the quadratic formula if necessary. This is quadratic in nature, so we have p squared and p squared. So we, for 40, 4 and 10. And so this p plus 2, p minus 2. And since they want real solutions, we can set this p squared minus 10 equal to 0. We get p squared is equal to 10, or p is plus or minus root 10. This is one kind, since we want real solutions that includes irrational, you will see them go ahead and factor this p plus root 10, p minus root 10, and you can do it that way for the factors. So the solutions are plus or minus 2 and plus or minus root 10. Example 3, list the possible rational roots. So we have this rational root theorem. And if you have a polynomial that has integer coefficients, so we have a 1 in example 3, a 1, a -14, and -24. Those are all integer coefficients. Oops. Then every rational solution, just the rationals, it doesn't include the irrational, but the rational, and so rationals are numbers that can be written as an integer over an integer. 5/4 is an example. 2/3 is an example. The number 7 is an example because 7 can be written as 7 over 1. Those are rational numbers. And it just happens to be that the rational solutions are the ratio of p to q, where p are factors of the constant term. So if we look at example 3, p in this case is that -24, or the constant is, I should say, -24. And so we would write factors, p are going to be 1 times 24, or 2 times 12, or 3 times 8, or 4 times 6. Those are all the possible factors of 24. And on all of these, they're going to be plus or minus. And so those are the things that are going to go in the numerator. In the denominator, we have factors of the leading coefficient a sub n. And in this case, a sub n is 1. A sub n is 1. A naught is -24. So for q, the only factors of 1 are just 1. So this is how I want it done on list the possible rational roots. You list the factors of p, you list the factors of q, and then you write P over Q, you have all of these plus or minus ratios of these numbers. 1 over 1 is 1, 2 over 1 is 1, I'm sorry, is 2, and 3 over 1, because the denominator on this is 1, those are all my possible rational roots, and they're plus or minus on each one of those. So just for a quick example, say that we had f of x is 6x cubed minus 2x squared plus, we'll say just 3. Then 3, factors of 3 are 1 and 3. And for q, factors of 6 are 1 and 6 and 2 and 3. So P over Q become all these different possibilities of where I put 1 over 3 all over 1, 2, 3, or 6. So that P over Q is 1 over 1, or 1 over 2, 3 over 1, or 3 over 2, and then 1 over 3, or 3 over 3, but 3 over 3 is 1 and we already have that, and then 1 over 6, or 3 over 6, which is 1/2, which we already have. So just to give you one more example of how we're coming up with these lists of possible rational root theorems. So you need to show work just like that to come up with them. In example 3, because the coefficient of x cubed is 1, the list seems simpler because all of the factors of p over the factors of q are just going to be the factors of p. So anyways, now what we're going to do is synthetic division. And we're going to try and whittle this down because this did not factor, I didn't talk about it, but it wouldn't have factored by grouping. And so that means we have to try some other things, and we're going to use synthetic division. And I'm going to use a condensed version of synthetic division because we have to do a few of these trials. So I'm going to create a table. And I usually start with the easiest ones, and we start with, like with 1. So we're looking at these P over Q values. And so I'm going to start with 1. And at the top here, I'm going to put the coefficients of the polynomial. And basically what I'm doing is I'm going to take 1 into 1, 1, negative 14, negative 24, and do synthetic division. But I'm not going to, I'm just going to show this last row. So if I bring down the 1, I'd have a 1 times 1 is 1, add, I have 2, 2 times 1 is 2, I have a negative 12, 1 times a negative 12 is a negative 12, and I get a negative 36. That did not come out to 0, so 1 is not going to be one of my rational roots. But instead of doing all this, I am just going to write down and do it in my head. If I bring down the 1, 1 times 1 is 1, plus 1 is 2. 1 times 2 is 2, plus a negative 14 is a negative 12. 1 times negative 12 is negative 12, plus negative 24 is negative 36. So I'm just doing synthetic division, but I'm doing it without writing all of the work down. So, well, that didn't give me a 0. The whole idea is I want to find one that gives me 0, then I'll have a reduced polynomial that'll be quadratic that I can factor or use the quadratic formula on. So it's because it's cubic and doesn't factor by grouping, I've got to find one rational root to whittle this down so that I can work with it. So I tried 1. And so if I do negative 1, again, I am just doing it in, I'm going to do it just in the chart. Bring down the 1, and 1 times negative 1 is negative 1 plus 1 is 0. Negative 1 times 0 is 0, plus a negative 14 is a negative 14. Negative 1 times negative 14 is positive 14, and negative 24 is a negative 10. That's the same thing. You can, right here, if I brought down the 1, multiplied, added, oops, I forgot to change it to negative. So I bring down the 1, multiply, negative 1 gets 0, negative 1 times 0 is 0, bring, add, multiply, and add. So I'm just saving the steps of writing that down. So we're doing kind of a condensed version of synthetic division. Because this is -10, -1 is not a root. So then I move on. So I try number 2. I try 2. Bring down the 1. And again, doing synthetic division. 2 times 1 is 2, plus 1 is 3. 2 times 3 is 6. Plus a -14 is a -8. 2 times a -8 is a -16, and -24 is a -40. So that did not work. Try -2. Bring down the 1 times -2 is -2, and add 1 is a -1. Times -2 is +2, and add is a -12. And -2 and -12 is +24 plus 24 finally is 0. So now you need to write down what this means. This is what you needed to happen, is get to where one of those is 0. And so since -2 was a root, then x plus 2 is the factor of this. So I have x plus 2. And then right here are the coefficients of the reduced polynomial by 1 degree. So it'll be a 1x squared minus x minus 12. Write all of this down, work down the page, have equal to 0, show the factorization. And for a minus 12, we have a -4 and a +3. So my solutions are x is equal to -2, 4, or -3. And that is the work that you need to show. You need to list all the possible rational roots, which I did here. You need to show this condensed synthetic division. Not that you can't show it this way, but that's just going to take up more space, but just trying to get you to use something that will be a little more efficient there. All right, example 4. Find all real zeros. So list all the possible rational roots. So your constant term, your constant term A naught is 4. Your leading coefficient A sub n is 6. And so factors of P are 1 times 4 or 2 times 2. And factors of Q are going to be 1 times 6 or 2 times 3. And so your list of P over Q, you have your 1, 2, 4 possibility over 1, 2, 3, 6. So you have to take 1 over each of those for your list. So you get a 1 over 1, a 1/2, a 1/3, and a 1/6. And then a 2 over each of those. So 2 over 1 is 2. 2 over 2 is 1. We already have that. We have a 2/3, 2 over 3. And then 2 over 6 is 1/3. We already have that, so we don't need to do that one. And then 4 over each of those. 4 over 1 is 4. 4 over 2 is 2. We already have 2. 4 over 3. And then 4 over 6 is 2/3, but we already have 2/3, so we don't need to list it again. And so here is the list of all my possible rational roots, which is required. And so then we can go into synthetic division in that tabular form. And so we have our 6, -11, -16, the 2, and the 4. Make sure you have all descending powers, 4, 3, 2, 1, 0, that if you need a 0 placekeeper that you do that. And we start with 1 and bring down the 6 times 1 is 6, and -11 is -5, times 1 is a -5, and -60 is a -21, times 1 is -21, and 2 is a -19, times 1 is a -19, and 4 is a -15. So that didn't work. If I try -1, bring down the 6, -6 and -11 is a -17, -1 times -17 is 17, -16 is 1, times -1 is -1, plus 2 is 1, -1 and 4 is 3, and right there, start with something else. So if I try a 1/2, if I bring down a 6, 6 times 1/2 is 3, and a -11 is -8, times 1/2 is a -4, and -16 is a -20, 1/2 is a -10, and 2 is -8, and ½ of -8 is -4, plus 4 is 0. Yes, I got that reduced. So right now I have my f of x is 6, and I want to see this, how it's factoring out. And we're trying to find the zeros. So if I have x plus 1/2, so my root is x is 1/2, my factor is x minus 1/2. And so this is going to factor x minus 1/2 times, then I have this 6x cubed minus 8x squared minus 20x minus 8. And so now we want to basically make this as my chart and work with a 6, -8, -20, and -8 and take things into that. Actually, I think what I'm going to do is redraw that. Now, what I'm going to suggest, when you get a lot of these rational roots, you could see that there's a lot of trial and error. Why do I not pick 1/6? Why don't I pick 1/3? Why not 4/3? Why not 2? Why not 4? And technically, you're doing this and you don't have access to a graphing calculator to do this. That's why we are learning, how to analyze these without that need to use Desmos or something. But sometimes when the list gets really crazy long and you've tried quite a few things and things aren't just working, then, go to the graphing utility and see if you can figure out one of the roots. So in other words, I'm going to go to Desmos and I'm going to graph this. And I'm going to look at because a root is where it's crossing the x-axis. So I'm going to switch over to Desmos, and there I have this graph. And we just found out that 1/2 was a 0, a root, and it gave out the y coordinate of 0. And so we've got that factor. So now I've got these other two. There's one here at -0.7, and there's one here at 2.732. And I think, I don't know why that's not last time when I did it. Yeah, there we go. -0.667. It had rounded it to 1 decimal place. I just needed to zoom in to get some more. And, oh, I see. I'm just hitting something that's not the 0. That's all. There's 2 of them in there. Isn't that crazy? So over here, we have -0.667, and here we have 0.7321. So that 0.7321 isn't a number I know, but the -0.6667 to me is a -2/3. So now that I've kind of identified that, and then I had another one over here, but that's also a number I don't recognize as converting to a rational number, I'm going to go back and look at this -0.667 as a -2/3, and that gives me some direction as my next value I want to try. So bring down the 6 times a -2/3 is a -4, and a -8 is a -12, times a -2/3 is a +8, and a negative, see, so 2/3, yeah, 3 goes there, 4 is a -4, and I was expecting this to come out a little different. Let's see. Did something wrong here. Let's try this again. So 2/3 times 12 is 8, and a negative 20 is a negative 12. And so once again, we get 8, and a negative 8 is 0. All right, so there you go. Negative 2/3 is a factor, or is a root. So that means we have x minus 1/2, and then we have a x plus 2/3, and that reduced polynomial, you have a 6x squared minus 12x minus 12. And so we're going to continue to factor on this. And I notice that each of these have a 6. I'm going to pull that 6 out here, because that will have numbers that are easier to work with. And I can try factoring x squared minus 2x minus 2, but it is not going to factor under the rationals. And those were those two values of what, points, something like 0.732 or something like that, negative, positive, on that graph. If we go back to here, over here we have that negative 0.7321, and over here we have over at 2.732. Those are two zeros that are irrational. The rational root theorem won't help you find those directly, but now that we have whittled this down to an x squared minus 2x minus 2, I can continue to solve this by setting this equal to 0 and using the quadratic formula. And this is subtracting, so 4 plus 8 is root 12. And you have 2, that's going to be 4 times 3, or 2 root 3 over 2. So my other roots that are my real roots are 1 plus or minus root 3. So my solution set to this is x is 1/2, negative 2/3, and 1 plus root 3, and 1 minus root 3, which you can write them together as 1 plus or minus. And if I take those values of 1 plus root 3, I'm going to be at that 1.723, and 1 minus root 3 at the 0.72, negative 0.72. Those are those two irrational zeros of this polynomial. But we needed to whittle this. It was a degree 4, and I don't have ways, we don't have we have a quadratic formula for quadratics of degree 2. We don't have something like that for a degree 4. So I needed to find a couple of rational roots to get it down to reduce something that's quadratic, so I could use the quadratic formula for the irrational roots. Again, this is the idea. This is not to go to Desmos to find all of the zeros. The idea is to list the rational roots and start going through to try to get to find one that gives you a remainder of 0, meaning that is like such as we did here with 1/2. We got a remainder of 0. That means 1/2 is a root, and x minus 1/2 is a factor. And then keep whittling it down so that you can get it down to a quadratic that either factors, or you can use a quadratic formula on. Again, yes, I went to Desmos because sometimes when the lists are long, it just seems to make sense to whittle it down, make that connection, but that's not my first go-to on these. All right, then we have the irrational conjugates theorem. And for the irrational conjugate theorem, if we have a polynomial with rational coefficients, and we have a and b are rational numbers such that root b is irrational, such as root 3, root 7, things that are not perfect squares. If a plus root b is a 0 of f, then a minus b must also be a 0. So let's just go to the example and apply this. Write a polynomial function of least degree that has rational coefficients, so that means this theorem applies. A leading coefficient of 1 just means it doesn't have some other vertical stretch to it, and zeros of 2 and 3 plus root 7. Because it has rational coefficients, you have to just apply the irrational conjugates theorem and know that 3 minus root 7 must also be a 0 of f. So they gave you 3 plus root 7. You have to be aware of the irrational conjugate theorem that since this is a polynomial with rational coefficients, 3 minus root 7 must also be a 0 of this function. So here is the process. You identify the zeros, all of them. And that means your factors are x minus 2 and x minus the quantity 3 plus root 7 and x minus the quantity 3 minus root 7. So that means my polynomial is going to be x minus 2, x minus 3 minus root 7, and x minus 3 plus root 7. And now you are going to multiply these out. But there's a trick to be able to multiplying these out a little bit easier. And yes, there are programs that will just multiply these things out for you and just spit out the answer. If you don't have multiple steps on these, you will not get credit. You will not get credit. And so one of the keys to being able to multiply this better is you must multiply these two quantities together first. And as you do it, the best way, and the way that I'll know that you have an understanding of how these multiply out, is you regroup those with this x minus 3 in its own set of parentheses and the minus root 7 and plus root 7 on the outside. And then right now, I'm going to think of this as my a is x minus 3 and my b is root 7, that I have an a minus b and I have an a plus b. And the reason is that those multiply to be a squared minus b squared, but my a is x minus 3 squared and my b is root 7. So those two quantities, this is the fastest way to be able to multiply them, is recognize it as a sum and difference. And so that when you multiply them, you just get that a squared minus b squared. So I'm going to get rid of some of this, go back and re-listen to that, kind of see that pattern. But when I know that, then I can say, oh, these are going to multiply to be that a quantity squared minus that b quantity squared. And then show the step where you multiply that binomial, square it, multiply and double it, x squared minus 6x plus 9, and then minus the 7. So then we have x minus 2, x squared minus 6x plus 2. Now you need to keep on going. Notice all the way down I'm carrying these equal signs. I started with it being equal to f of x. You need these multiple steps to work. Now I'm going to take x times all three of those, getting an x cubed minus 6x squared plus 2x. And I'm going to take the minus 2 times all three, minus 2x squared plus 12x minus 4, and collect like terms. And this is equal to, you need a polynomial function, you need the f of x equals, or you don't get credit for it. And you need all these steps. To show that you actually are multiplying them out and not just having some other program do it for you. So now go back and read. It said a polynomial function of at least degree, just meaning I don't want to have it, if there's 3 zeros, it should be of degree 3, nothing higher. And the leading coefficient of 1, which it has, and those are the zeros. So that seems to be good.